Present, sir.
Ashif,
Present, sir.
Hitan,
Present, sir.
Shrikama,
Present, sir.
Nilanjan,
Present, sir.
Shabul,
Present, sir.
Girish,
Present, sir.
Shukurna,
Present, sir.
Shanton, Shanton, Vivargo, Orkutjyoti,
Present, sir.
Onat,
Present, sir.
Pritam,
Present, sir.
Medha,
Present, sir.
Arnav, Seyosri,
Present, sir.
Rishi,
Present, sir.
Shishmita,
Present, sir.
Shruti,
Present, sir.
Anuraj,
Present, sir.
Pranav,
Present, sir.
Shomili,
Present, sir.
Shaurin,
Present, sir.
Akash,
Present, sir.
Mandash. Manda's problem of mic will not be solved, huh? Aditya,
Present, sir.
Anirban, Shurojit,
Present, sir.
Ruktoy, okay. All right, so as you said that this part has not been covered in the previous semester, particularly finding the lattice energy of ionic compounds when ionic compounds are present in lattice in the form of bulk. So as all of you know that ionic compounds, they are formed by electrostatic attraction between the oppositely charged ion and a balancing force where the repulsion between the similarly charged ions and their combined effect results in an optimum distance at which the cations and anions come together and form ionic compounds. As all of you know that ionic bond is a very strong bond, and as a result ionic compounds often show high melting point. They are hard in the molten state, they show electrical conductivity, and they are soluble in polar solvents because of dipolar nature of these ionic compounds. Now we talk about, when we talk about ionic compounds, the ionic compound doesn't mean that you have only one molecule that is present. So one molecule, when you talk about an isolated molecule, then that it might exist in the gas phase. But even in the gas phase also, there is some sort of interaction with each other. But as you go more to the condensed phase, that means either in the liquid or in the solid phase, then the stability of their crystalline structure increases, and the energy that is required, or rather I would say to break a lattice, is something called a lattice energy. And this lattice energy, if you want to dissolve an ionic compound in a polar solvent, just a second. হ্যাঁ তাপসদা, হ্যাঁ ক্লাসে আছি, ধরুন 12টার দিকে। ঠিক আছে তাপসদা, ওকে ওকে, sorry. So, and this lattice energy, which is formed in the bulk state of an arranged structure of these ions in the condensed phase or in the solid phase, has to overcome in order to dissolve an ionic compound in polar solvent. And this lattice energy that depends on different thermodynamic steps that are involved in converting the reactant elements into the crystalline product. So this is one which is an experimentally, just by doing thermochemically, one can find out the lattice energy, or lattice energy is dependent on the, since it is dependent on the Coulombic attraction of ions and the geometrical structure, theoretically one can find out the lattice energy as well. So we shall see with a prototypical example of sodium chloride that how we can find lattice energy experimentally and how we can find out the same from a theoretical approach. So when we talk about the energetics of ionic bond, the energetics of ionic bond you can think of as an example of sodium chloride formation. So if you take the sodium metal from its elemental form, chlorine in its elemental form, and if you form a sodium chloride solid form, so this overall reaction from sodium and chlorine form sodium chloride in the condensed solid phase, the heat of formation is about 14 kilojoule per mole. But as you can see from this particular reaction, that you have sodium in its elemental form, whereas on the right hand side in the lattice, in the solid state, sodium is in plus ion because it's an ionic compound, Na plus. Similarly, chlorine is in the elemental form, and on the right hand side you have chlorine in the negatively charged. So you can think of that what are the different steps involved in the formation of sodium chloride from the elemental form like sodium or chlorine, and then can find out the energy of each and every step, and you can find out then the formation of energy. And this can be experimentally find out from the thermodynamic cycle, and you can get this, that when you have ions in the gas phase and then in the ions in the crystal lattice, the energy difference is attributed to the lattice energy. Again, when you think of that elements, for example, in any form, whatever the elements, the starting compound like sodium or chlorine, let's say you have a reference point here. So obviously, the heat of formation, just like the example here, is about minus 414 kilojoule per mole, is the energy difference between the elements in their reference state and the ions in the solid phase. That means in the lattice. So this is the energy difference. But what are the, as I said, that you need to really work on the different steps and the energetics associated with these steps in order to find out the total energy associated with the process, and then you can get the overall energy of the solid. So what are the different thermodynamic steps that you can think of when you make sodium chloride? You start from sodium ion, sodium in their elemental form. So sodium in its elemental form in the solid. You have to make sodium in the gas phase. So you now have, this is something called an energy that requires to sublime the sodium from solid state to gaseous state. Then the next stage that requires is the ionization of sodium to sodium plus. So this is the first ionization energy of sodium. So you may consider the ionization energy of sodium in this step. So now you have energetics, that is sublimation energy and ionization energy. This is the sodium part. Now if you go to the chlorine, which is in the gaseous phase, first you need to, because chlorine is a diatomic gas. So first you need to dissociate the chlorine from diatomic to its monoatomic form, like, because in sodium chloride you have only one chloride anion. So if you go back from sodium chloride, Cl minus, then you have to go to Cl in the atomic state, gaseous state, which is an ionization process, and then from the gaseous state to its chlorine atom to a diatomic chlorine gas. So first you need to dissociate the chlorine, and then you have Cl to Cl minus, and you know this is nothing but electron affinity. So chlorine will accept electron and it will form Cl minus. So effectively, this is the state which liberates energy. So here, this is an electron affinity. And now if you combine this sodium and chlorine together, what you are getting? So sodium and chlorine, you are going from sublimation of sodium, ionization of sodium, dissociation of Cl2, electron affinity of Cl, and that forms a gas phase Na plus and Cl minus. And then from Na plus, Cl minus, and going to sodium chloride, that difference is actually your lattice energy, because it goes from a gas phase to its condensed phase, and one can think of finding out this lattice energy accordingly. So if you just step by step think of that, what are the different energy that requires to form sodium chloride. So look at this. First step, what I said, is the ionization of sodium. From sodium, you can have metal to gas vaporization is the first step. Okay, this is actually should be the first step, but anyway. So the vaporization step of sodium metal to sodium gas is about 109 kilojoule per mole plus. You need to provide this energy in the form of heat. The second is the ionization of sodium. So sodium will now from the gas phase to form sodium ion, and this is an ionization energy, and the energy requires for this ionization process is about 500 kilojoule per mole. Similarly, the dissociation of chlorine requires an energy of 242 kilojoule, But since you are forming two equivalent of sodium, two equivalent of chlorine atom in the gas phase, the overall dissociation energy, this is for two chlorine atoms. For sodium chloride formation, we really need to normalize it. So therefore, the value will be half of this. That means 121 kilojoule. And then the electron affinity of chlorine atom in the gas phase to the chloride anion is about minus 364 kilojoule per mole. Now, if you add them up, all of them, eventually what you find, the total energy of the reaction, associated reaction, although you have this one, you have a negative value, minus 364, but this is already high positive value. Therefore, total, if you just take them and sum them up, still the energy associated for all these steps is about 364 kilojoule or more. So the question is that the Coulombic attraction of the reaction products which are of opposite charge and the energy associated with the formation of the solid state chloride we have not considered yet. So the two ionic species, sodium and chloride ion, which are originally at zero energy, they attract each other with accompanying energy change. They should decrease their energy and overall they should get stabilized. So how you can explain this? For that, you really need to consider the Coulombic interaction between now. So the now initial thing is they should form first the ion pair, right, in the gas phase. So ion pair means sodium and chloride will come and form pair. And for that, the Coulombic interaction has to be considered of the opposite charged ions. And as you know that they attract each other, sodium plus and Cl minus, and the associated energy can be expressed by Coulomb's law. All of you know this very well. And this value of R is the interionic distance. And here this is the electron charge, epsilon 0 is the permittivity of the space, and like the vacuum, and Q1 and Q2 are the charge of the two ions. But as you know that when you take in the gas phase, you have sodium ion and you have a chloride ion. Assume it's far apart. But you are bringing in together, close to each other. So as you decrease the distance, absolutely the Coulombic interaction will increase, and that will contribute to the energy, which is that energy of the system will go down. But as you bring them very close, then what will happen? There will be an electron-electron repulsion. And this electron-electron repulsion will depend on the distance and obviously the nature of the ions. So how you are doing this? So you have a core electron of the cation, the core electron of the anion. As you bring and come close together, the electron cloud of this will now feel a kind of a repulsive force from the electron cloud of the other ion. Even if they attract each other, the electron-electron repulsion force will also work. So effectively, the green line, as you can see here, this is the electron-electron repulsion. And as you bring them very close, the repulsion force increases. And the repulsion force is expressed by this term, which is P over R to the power n, where n is something of an exponential value, so which is called a Born exponent, and this exponent value is dependent on the nature of ion. And now B is a constant, and here if you put the Coulombic interaction overall, you can then write out that the attractive force and the balancing repulsive force eventually bring the two ions at an optimum distance where they balance each other, and in fact the system arms stability, and the distance at which this will form a stable system is something at the low energy of this value, which is an average one, the balancing energy graph, which is in the yellow. So at this distance you can see that your energy is the minimum. But if you again try to bring, the repulsive force dominates, and then again they will be destabilized. So if you consider these two different type of forces that are working, the Coulombic force, that, as you have seen, that decrease the overall positive energy. However, that will not make any change in the sign from plus to minus, because sodium chloride molecule in the gas phase formed are not the final reaction product. That the reaction would occur if delta HT remains positive. So even if this energy is considered, it's not enough to overcome this difference already that we have by adding so many different terms. So in the gas state, the electrostatic force, they are not saturated because they remain active in all possible directions. However, when you bring them together, several such ions come together. Now there will be an ordering of these ions, and this three-dimensional ordering, which is called the crystalline solid, eventually dominates, and that dictates the overall stability of the solid in their condensed phase. So if we just very simple mathematics, that we now have a total energy associated with the Coulombic forces that work on the two ions, that can be expressed as the Coulombic attractive force and the repulsive force. But we have seen that the equilibrium distance, which was actually the R0, that means now at that point your dE, the total energy change with respect to the distance, will be 0. So dE over dR will be 0 at the equilibrium distance, or the optimum distance, what you consider as the bond distance between the two ions. And then let us consider that is R0. So if you consider R0, then you can just take a derivative of this one. So you get dE over dR at R0. That will afford E square over 4 pi epsilon 0 into R0 square. And now from here, now you get a negative sign. Now you will have an NB of 4 pi epsilon 0 R0 into N plus 1. So you take the first derivative, and at that point the rate of change of energy with distance will be 0. And now if this is 0, then you get the value of B from here. Just by solving this equation you can find out the value of B, and that B is E square into R0 power N minus 1 over N. Now if you just put that this B value in this equation, so you put E0, that means at equilibrium distance, the Coulombic force, the overall Coulombic force, the total energy associated with the Coulombic force will now be minus E square over 4 pi epsilon 0 R0, plus you put the V value of here, then you just adjust all other parameters like R0 and all, you get E square over N times 4 pi epsilon 0 into R0. So you can write it now, take E square by 4 pi epsilon 0 R0 as common, you get 1 minus 1 over N. Now, if this is the energy, if it require to find out that, okay, here, this is the Coulombic energy that is associated, where the two ions come close together and the energy it contributes there. And this value will give you an overall change in the reaction in the solid state. But the question is, here in this case, does not take into consideration the other ions from where it can face a kind of attraction and repulsion forces when many ions come close together. So when many ions come close together and form a lattice, you really need to find out that overall you can find out that heat of formation HF. Now if you add all the values like sublimation, ionization energy, dissociation and electron affinity, plus this is something called the lattice energy, then you get your heat of formation. That's about minus 411 kilojoule per mole. But here, will this give you the lattice energy calculation, the value of the lattice energy? So theoretically, how can we find out? Experimentally, you can find out this value. So all these values you can find out experimentally what is your lattice energy. But can we really find out theoretically what would be the lattice energy? And if you can find out the lattice energy, the other values for all ions you can find out experimentally, and then you can find out the heat of formation of any solid from its heat of formation of a particular solid in the solid state from its atomic species. Here, you basically take care now of other parameters that we have seen that, okay, we have considered charge of the two ions. We have considered the distance between the cation and anion, the constant M, which is dependent on the ion or elements that are forming the solid. So, but what we have not considered yet, that what about from this equation? It's basically the same, right? The only thing is that there is something which is missing from the Born-Lande equation here. So Born-Lande equation was developed just to find out the lattice energy theoretically, which takes care of other constants like Avogadro number and a value which is M. And how do you find this M? How they actually got into this M, which is something called a constant, and this is called Madelung constant. This, when you consider Madelung constant M, an Avogadro number, that means it is not only considering two ions in the solid, but it is considering a large number of ions in a condensed phase. When they are ordered, they are arranged in an ordered fashion, which is called crystalline lattice. Now Born came up with this equation based on certain very simple mathematics derived from this part, which we have just seen from the Coulombic forces, and this part is from the arrangement of atoms in the lattice. Now, how this lattice energy is dependent on this M, this constant, and how one can really get information about this constant M, which is the Madelung constant. For that, you really need to understand how solids are formed, and they give rise to enduring structure with beautiful arrangement of atoms or ions in the lattice. So cesium chloride, let's say you have a cesium chloride. I will come to sodium chloride soon. They form many different anions, the alkali metal halides. More or less, all of them form very similar kind of lattice. Although there is a difference in size of the cations, and obviously when you have chloride, the anion size remains same. You have cesium and you have chloride. Now, if you have cesium, one type of ions, if you consider a cube, cesium is the big ion. So cesium is one type of ion that actually occupy at the corner of a cube. So now you have in a lattice, when they are arranged in an ordered fashion, each corner of the cube is now occupied by cesium or one ion. You can consider the cesium first. The other ion, which is chloride, that occupies at the center of the cube. If you consider cube as the cell, okay? So cell means is a unit of a solid lattice, which is a repeating unit. So one cell, after that another cell, after that another cell, just like cell in living organism. In solid, crystalline solid, the unit cell is a unit of the lattice, and that's why they are called unit cell in crystalline material. So the other ion, like chloride, it occupies the center of the cube, and this way the lattice grows. If the lattice grows, let us now consider the sodium chloride. So this is more like a sodium chloride. You again have two kinds of ion, sodium and chloride, and here again the sodium ions occupy the corner of the the corner of the cube, and also the center of each face. So if you just look at, you have, okay. So you just see that sodium ion first occupy here, 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 and here. And then also on the face. Face means if you consider cube, you have again 1, 2, 3, 4, 5, and 6 faces you have. Now, middle of the face is this. So they will occupy the face as well. The corner and the face and the other ions, they occupy at the center of each edge and the center of the cell. So if it occupies the center of the cell, that means middle of the cell, and also at the edge. Edge means this, here, 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 and here. And since the ions, and this way it repeats, and the repeating unit form the lattice. So you will find that every sodium ion will be surrounded by a certain number of chloride ion, and every chloride ion will be surrounded by a fixed number of sodium ion. And this is something called a face-centered cube. So you have a face and it will form this kind of lattice. There are other form of lattices which I don't want to go into this right now. Maybe I'll discuss this next class, different other kind of structure. But what we were interested to find out that how sodium chloride structure is formed. So if you consider a two-dimension, here you see that your sodium, you can put it in the corner, right? In a two-dimension, first you consider, and then we'll go to three-dimension. So sodium chloride, you put one sodium in the corner. So if sodium occupies one corner and you have the others, you can, in the face, you have these chloride ions. So how many chloride ions are there? You have 4, assume, surrounding it. And then you will have one towards our front in 3 dimension, and in 3 dimension, there will be another one at the back. So effectively, 1 sodium is surrounded by 6 chloride. But in 2 dimension, let us first see what is happening. You have 4 chloride. Now, this one, we have to find out the sodium and chlorine. These 2 ions, you can find it out from the attractive forces. Whereas these 2, there will be a repulsion. And that part we need to consider. Exactly at what distance? If this is a unit cell, and if I consider this is 1, and this is 1, what is the distance between this and this? Quickly, the 2 anion, distance between the 2 anions. If this is unit, what is that? And this one?
It's √2.
Okay. So if this is the distance, so you will have a square root. You can find out that this is a diagonal of this one, right? So you can find it out how many different such kind of ions are there. Again, there will be an interaction, and this way you can have this kind of interactions, that the repulsive forces, attractive forces, repulsive forces at different distances, and you get this kind of series. This is, since at every distance, like at unit distance, and then 2 unit distance, then 3 unit distance, 4 unit distance, 5 unit distance, and this way you basically can find out how many different ions are interacting with each other and what is the total attraction force, attractive force, and repulsive forces that is formed in the lattice, and you get this kind of series. This is, you can get it from 2 dimension. But let us see what happens in 3 dimension. So in 3 dimension, again, in every direction, you see 1 sodium at the center, and you now have in 3 dimension, just like an octahedron first formed, all 6 will occupy the chloride around the sodium ion. Now, if you have this way the lattice grows in 3 dimension, in every direction, right? X, Y, and Z direction. And this forms a lattice of sodium chloride in solid state. So if you now consider that in 3 dimension now, you will find that there will be 6 chloride against, at a unit distance, you will have 6 chloride against sodium. So you have an attractive force. Then at distance 1, you will have, where you had 4 chloride, now you will have 12 such chlorides because you are considering a 3-dimensional structure. And then at unit distance 2, 3, 4, this way if you can go continuously, you will keep on seeing that there is a kind of a series that is forming. So this infinite series is actually mathematically, when this Born and Lunde, when they calculated this mathematically, they find out that it actually converges to a value close to a 1.748 for sodium chloride. But this is not fixed for all ionic structure. This is a value that can vary depending on what are the different ions involved in the lattice. So therefore, you can find that the Madelung constant M, which was considered in the Born-Lunde equation to find out the lattice energy, this M value that we see here from this series, that we can get an overall energy of the lattice by using this equation, where we should know about the distance between sodium ion and chloride ion. And the Madelung constant for sodium chloride is 1.748, whereas cesium chloride, since the distance is different between cesium and chlorine because of the weak size of the cesium, and therefore the Madelung constant is more or less very similar, slightly different because of the difference in the distance. Zinc sulfide has a different structure, and therefore you see the value is different. Calcium fluoride has a different structure, and therefore the lattice orientation is different. Interaction of one ion with another ion in three-dimensional direction centered around the cation, what kind of Coulombic attractive forces and repulsive forces are operational there. These will vary, and therefore Madelung constant will vary. So the Madelung constant is dependent on the nature of the lattice, and when you have known structure of the lattice, one can calculate the Madelung constant. If it is, one can find it out. Otherwise, you know that, okay, for a specific structure like, a cubic structure of sodium chloride, you have Wurtzite structure. Like for zinc sulfide, you have fluoride structure for calcium chloride, and then so on and so forth. Each one has a different Madelung constant. So you have a Madelung constant for a particular structure. You have Avogadro number. You have constant value 4 pi epsilon 0. You know the charge of the constituent ions, sodium and chloride. You know the charge, electric charge, and you know the distance between the cation and anion, which is basically the optimum distance r, and then 1 minus 1 over n, and this n value, as I said, this is a Born exponent because this value is related to the size of the atoms or size of the ion. The bigger the size it is, that means the repulsive forces between the two ions will be more even at a longer distance, and as a result you have your distance will be different. So you have this the Born exponent n value is also dependent on the ions involved, and you have these values for every ion fixed. You can take those values and you can put this in equation, and then theoretically you can find it out what is the lattice energy. Now, if you get the lattice energy experimentally from the thermodynamic cycle, and if you just compare with this, more or less they match within the order of certain error percentage, and you can use this Born-Lunde equation in its different form. I mean, I'm not saying that Born-Lunde equation can always be predicted. You can always find out the lattice energy from the Born-Lunde equation. Lattice energy, experimentally you can find out the way I have shown. Theoretically you can calculate, but here you see that it requires an understanding of the structure. You need to know the distance, which is an R0 or D, whatever you call it. All this, that means you should have an idea about the structure of the solid in its solid state lattice form. If you don't have a known structure, then what you will do? Yes, experimentally you can determine, and then you can theoretically try to find out whether any modification of the Bond-Lande equation is possible or not. So Bond constant, as I said, the ion configurations, the n value, which is the Bond constant or the Bond exponential function. The larger the ion is, the repulsion is more, and therefore the value is increasing with the configuration of ions as it increases. And these are the values. You can find it in the textbook. And I would recommend you for this part and also the part that I covered in the last 2 lectures, please read the book on inorganic chemistry by Hui, Keter, and Keter, James E. Hui and Keter and Keter. So this is a very good textbook, and most of the things that I covered are actually from there. And just read in between lines from that chapter. So this is basically the 4th chapter.
So can you please write the name in the chat box?
Yeah, I'll do that. So if you have you can compare that how melting point changes with structure, and you have, depending on the nature of ions involved, depending on the size of the ions, the lattice, and all these parameters will dictate the melting points. And here you see that not only that ionic charges are important, but the interionic distance is also equally important. Here interionic distance is decreasing, where a charge remains same compared to sodium chloride, where sodium and chloride ion, the interionic distance, or which is the optimum distance, R0 or D, whatever you call it, the melting point of sodium chloride is about 800 degrees Celsius. For sodium chloride, both the charge of the cation and anion remains same, just like sodium chloride, but the interionic distance decreases. Structurally, they are very same. So Madelung constant will not vary. So what is the factor here? It is the interionic distance, which is the responsible for it to show higher melting point, as expected, because you need more energy. So to break the lattice indicates that the lattice energy is higher in case of sodium chloride. Now, if you go to magnesium oxide, your magnesium is in +2 state. This is oxide, again -2 state. So Q and Q plus, Q minus charge, these are now dominating. If you compare the distance, this is also decreasing. So both are in favor of a higher value of lattice energy. And as you can see, the magnesium oxide melts at about 2800 degrees Celsius. So it's a very strong lattice of magnesium oxide. Calcium oxide, if you go, obviously interionic distance will increase because its size is increasing for the calcium. And since this one is increasing, obviously the value of lattice energy will decrease a little bit. And as you can see that it is about 2580 degrees Celsius. So all of them have very similar sodium chloride-like structure. So if you have a sodium chloride-like structure, then the other parameters will remain same. They will be only dependent on the charge and the interionic distances. And as I was telling, that this is fine with the compounds, the solid compounds where the structures are known. But there could be structures which cannot be crystallographically characterized, or X-ray data is not possible to collect. For there to gain an insight into the lattice energy, there was an equation was developed by Kapuscinski, who in fact worked on the lattice energy for ionic crystals, for the systems for which you do not know the crystal structure. So he modified the Bond-Lande equation, assuming that you have the distance, the optimum distance at which the two ions form an ionic lattice. The two oppositely charged ions, just by keeping a balance between attractive and repulsive force. It's not much different from the ionic radii of these two ions. So one can think of that the inter-ionic distance may be considered as the sum of the ionic radii of the constituent atom, or the constituent ions. So he said that the distance will be the positively charged and negatively charged ions, their distance. He, in fact, made a simplification of all the constant term and the number of ions in the lattice, that means in the molecule, that is also fixed for a particular solid. You know the charge, and again he put a value of 34.5 as a constant, which is, in fact, you get this from the equation. So 1 minus, instead of 1 minus 1 by n, this term, he put it that, okay, by studying a lot of structures, Kapuscinski found this empirical equation, and here he said that this also matches more or less within a certain very small deviation even for the known crystals, because his equation was dependent on the structures known and trying to fit the known structure first, and then one can really check with the unknown structures where the distance is not known but the constituent ions, ionic radii are known. You can fit in it and it gives you the lattice energy for an unknown system for which the structure is not known. So these two equations, right, like the Bond-Lande equation and the Kapuscinski equation, helps to find out the lattice energy, and particularly for systems which are experimentally difficult to determine, Kapuscinski equation works well. But the Bond-Lande equation for known structures, one can always find out the theoretical value of the lattice energy, which is based on the orientation of ions in the lattice and exactly at what distance you have you have attractive interactions and what distance you have a repulsion between the similar charged ions. Considering that, he found out, they formed this equation, which is the basis for a lattice, and experimentally both of them match very well with the theoretical lattice energy calculated by this equation. That's fine, but there is a problem in all these ionic lattice. We talk about ionic structure and assume that all ionic lattice or something which can form an ionic compounds, quote unquote ionic compound, I would say, because from very first day of learning chemistry, we know that the elements on the left hand side of the periodic table, like group 1, group 2, would tend to interact with the group 16, group 17 elements. and they form ionic compounds because of huge mismatch of electronegativity. And one can form cation, the other side can form anion, and therefore cation-anion interaction works well. But the question is, if you have, for example, consider an example of, we have discussed so much about sodium chloride. What about sodium chloride? What about calcium chloride? They have a different structure. Fine, no problem. But let us increase the size of the cation and go from lithium to cesium directly from the group 1. So you have lithium, sodium, potassium, rubidium, and cesium. So you go to the cesium, which is a bigger in size. But keep an anion, which is a smaller one, like fluoride. Will the lattice energy for such kind of solids be only dependent on the ionic systems that we have talked about? Or is it purely ionic? These are the questions that now comes to our mind. So if these are these questions, if you want to address, we need to know that not only these ions have different sizes, there is a huge mismatch of size. So in a lattice, it is more like, I told you this, it is more like you take a box, a square box, and you take big balls, right? 6 big balls. Put the 6 big balls there, or 1 big ball, or very small several balls. What would be the lattice energy there? Will the lattice energy be purely based on ionic interactions? Can we explain always? Because of different, if there is a size mismatch, if you have all the ions are of very similar size, then all the ions can fit there very nicely in the box. But if you have different ball sizes, then fitting the balls in the box will not be as compact as that of the similar sizes balls. So that means even in the lattice of ionic, so-called ionic compounds, there is not necessarily the lattice energy will be very similar. So which indicates that the cation size, if it is much bigger, that means you have a huge electron density. And if you have a huge electron density, and if the other ion is smaller, then there will be a kind of a polarization. The polarization means that the electron density on these atoms, on these ions will be distorted and very polarized by the other ion, the negatively charged ion or the opposite charged ion. In that case, there will be a certain percentage of covalency that will get in the system, and the overall lattice energy will be different than the lattice energy of the structures for which we have seen by using experimentally through thermochemical or by theoretical studies by Bond-Land equation or Kapuskin's equation can provide information about. So this ionic size and their orientation in the lattice, how they affect the overall lattice energy, that part we should learn. And once that we know, then we can really predict that for which system the lattice energy will be high, which system the lattice energy will be low, and that would help you to talk about which compound can be soluble in which solvent and which compound will have high melting point which solid have low melting points, and a proper comparison is possible in that case. As I have shown in few slides before, the sodium chloride like cubic structure, the compounds that show a very similar kind of structure like the cubic structure of sodium chloride, all of them show very similar structural lattice structure. Lattice structure means the one I have shown, that one cation, then you have all 6 reactions anion, and then again each cation is occupied, surrounded by 6 anions. Each anion is occupied by 6 cations, and this way the lattice grows. This is called a cubic lattice. Sodium chloride, sodium fluoride, magnesium oxide, calcium oxide, all of them show similar lattice, and you can compare their melting point because you know their interionic distance, you know the charge, because for Madelung constant is fixed for that kind of solid state structure. But Madelung constant will be different for different other structures, and therefore comparing with sodium chloride structure with that one may not be, may not be a good way. But if we can assume that the ionic compounds, along with the structure, which component of the ionic compounds is actually making this difference in their lattice formation, probably the arrangement requires adjustment but for some other interactions, and those other interactions are nothing but the effect of polarization, the effect of what is called the size dependent polarizability. So polarization can take place if ion is big. It is more like, if you have a big ball, the probability of getting it inflated is more. If you have a small ball, you need to have more force to inflate it. So this covalency factor in ionic compound we should consider, and once that part we know, then we can talk about more about their properties like the lattice energy accurately, melting points, and other parameters accurately. That we'll talk about in my next class. So I should write down the name of the books. ক্লাস করছি, একটু বসুন। আমি চলে যাচ্ছেন নাকি?
যদি আপনি চাটা খেতে চান,
আপনি আসছেন তো এখন?
দিয়ে আপনাকে বাড়ি থেকে যেতে হবে।
ও আচ্ছা,
যদি এই ডাক্তারের চিকিৎসা যদি না হয় তাহলে আপনাকে দিয়ে করাবো।
ঠিক আছে, ঠিক, নো প্রবলেম। What is the title of EARL? You got it?
Yes, sir.
Yeah, this is actually a very, very standard textbooks that you should follow, and you can have a copy of that, all of you, those who are interested in chemistry, because you should have a copy of this book. Because the other topics like the acid-base chemistry and redox chemistry that we'll cover in this course are also from. In fact, the intermolecular forces, the chemical forces that I discussed in the last two classes, you can follow from this book also. It's just a previous chapter. I think, no, I think the next chapter, chapter 5, I guess, if I remember correctly. So, all right, any question? Another point is that tomorrow at 9 o'clock class, I won't take, but on Thursday afternoon class, I'll take. Tomorrow, tomorrow, just after that, I have a master's class, so I cannot take both, just one after another. All right, so can you tell me your email address for where you can access the lecture notes? Is the same as the one you use?
Yes, sir.
Okay, so is that that Gmail address UG2021 or something? 2020?
Yes, sir.
Yes, sir. This is 2020.
That ISCS email you can access, right?
So that we can.
Yeah. Okay. So I'll just send the lecture notes so far. That would help you to understand the topic. And what else? I was trying to say something. Okay. So I think I already told you that these parts that I'm discussing will not be in your end semester, in your mid-semester examination. So mid-semester examination will only have topics covered in organic chemistry part. Oh, this is the Gmail address you want, right? Okay, so
Yes, sir.
ISCS UG. Yeah. All right. Thank you very much.
Thank you, sir. Thank you, sir.
Thank you. Bye.
Thank you, sir.